Hello everyone, today we are going to discuss on specific topics of complex numbers. Here we'll discuss about the definition, then we go for a little understanding about complex algebra, and in the last we will look at the geometrical representation in terms of sum, differences, product and quotient. So first of all, why do we need complex number? It is the basic question that always arises why we need this complex number, whereas we have real numbers, and then why we need some imaginary numbers. Suppose we have a quadratic equation in the form of ax square plus bx plus c equals to 0, and if the roots of this equation find we find the root of the equation in the form of just like x equals root minus 5 or x equals root minus 3, pause, or we have root in the form of just like root minus 4, and then we'll go for root 2i. So what is actually happening here, we'll getting this I that is not real, which is indicating that the root which we are getting is not real. Then what is actually it means? It means that the mathematics which we are using from a long years and years, that is not sufficient to solve such type of questions, so that we introduce a new term that is called imaginary number, which comes under the topic complex number. Complex numbers are represented as z equals a plus ib, where a denotes the real part and the ib denotes the imaginary part. We can also write z real part equals a and imaginary part of z is ib. So here we are going to represent these imaginary numbers. So let we have two axes, one is real and another is imaginary. So as we have discussed earlier, a plus ib equals z. So real part is a and the imaginary part is ib, and their resultant going to be this point, and it is denoted as z. So let's extend this idea. We have a module of z equals root a square plus b square, then we have square equals a square plus b square, and the last we got module of z square equals z and z complement. One thing is clear, we got here clear that the square of this module is nothing but what, the complex number as well as its complex conjugate multiplication. Again, let's extend this idea. So here we have a unit circle having a unit diameter. So what we have done here, we have taken a radius having angle theta, and we set some perpendiculars on the x-axis and the y-axis. So what we are going to do here, that we know the x coordinate give us r cos theta and the y coordinate give us r sin theta. This b1, this b2, dividing 2 by 1, we get y upon x, resulting in r sin theta by r cos theta, which result in y by x equals tan theta, and this will give us theta equals tan inverse of y by x, and this result is known as argument of the complex number. So now come to the last topic, that geometrical representation of complex numbers, sum and the differences. So how the sum going to be? So let we have two axes, one imaginary and one real, and we have two complex numbers z1 and z2. So their sum is very easy, that's nothing but the law of parallelogram vector addition. So what we have one line, that is z1, and the another along the varying axis, that is z2. So applying the parallelogram vector addition law, we will find this thing and this one, it is along this direction, and the resultant will find in such a way. So what we have get this, the line which is found here, which is the diagonal of this parallelogram, which is nothing but z1 plus z2. This is the simply representation of. Similarly, we will go for difference, but the only difference in between the sum and difference. Similarly, we will go for z1 into z2 as well as z1 by z2. Thank you for your attention, and thank you. I hope you will like this video. Thank you. Have a good day. Thank you. I hope you will like this video. Thank you. Have a good day. Thank you.